Okay, the final lesson in the nonlinear training manual, lesson number 8, is what we are seeing into. Oops, let me go to the right page here. It would be this one we saw. I thought I was at the right page, but it's okay. Here it comes. So lesson number 8, it is on metal forming. Many intricate and involved concepts have been covered in this topic. It could be different things like in terms of material, we are using elastoplastic material. There is geometric nonlinearity as well as large deformation, and most important, the new concept would be towards large strain. First time in this training manual, we are going to use large strain analysis. We are also going to making use of the advantage of the 2D simplification that would help us reduce the model size and faster analysis can be done. Typically, appropriate material model is used, and a refined mesh has been taken at the local locations. We ensure that the correct contact conditions are created. Obviously, contacts are one more kind of nonlinearity, and they have been imbibed in this one. Analyze some errors that may occur during a nonlinear. So typically we solve it with a default condition. We are seeing the most frequently seen errors that will come up, and thereon we move on into we make the appropriate improvements to do a proper analysis. And finally we post-process the result, and of course we'll interpret and analyze if the results are correct. So what is the setup? If you see here, this is a typical bending machine. There is a punch down here. There is this specimen. The die is giving the appropriate shape, and there is a load cell to measure the forces that are being applied. This is we have got this model from University of New Hampshire. Thankful to them for this image, as well as the some certain details that are necessary for creation of this setup. We need to understand that typically punches or these kind of sheet metal forms can have different kind of analysis requirements for different sizes, and even the materials behave differently depending on the size. So this university does a lot of research on that topic, and is adding value to this particular industry. So here is the analysis setup. So we convert this particular intricate setup into a basic one, which will capture all the necessary things, and our setup would look something as that shown in the picture below here, wherein we have the die, we have the specimen, and the punch. Okay. Further simplification has been done by using only a 2D geometry instead of this 3D. So we are doing the analysis on a 2D setup. So this is what this setup is all about. We are going to analyze it, and let's see how we go about it. So creation of a 2D setup is a new thing. So I'll quickly show you the option down here. So when you go into new simulation study, nonlinear, at the bottommost you will get this option of use 2D simplification. We select that. Okay. On selecting that, we are getting these different options of how do you want to treat the 2D. Is it a plane stress example? Is it a plane strain example, or is it an axis symmetric example? So depending on the idealization that we are looking at, we can select the appropriate setup. In this case, we are taking the plane strain setup and proceeding with the analysis. Okay. So if I get into the edit, the definition of this one, let me open it. Yeah, here it is. So we are taking the plane strain. We are selecting the appropriate plane along which the cut will be done, and we are giving a section depth to represent this entire geometry. Okay. So this is the basic creation of the geometry. We are using plane strain elements first time in this nonlinear training manual, and the process of creating it is like this. Material, the die and the punch is made up of alloy steel. The specimen which will be formed is actually of brass. Okay, so that those are the material details. If I get into one of those materials, or I think more important would be the brass material, I'll get into that. Because that is a place where we are doing some material related changes. So first of all, I think by now we all are comfortable with this word hardening factor, and we are giving the value of 0.85. So we are saying there is around 15% of isotropic hardening and 85% of kinematic hardening. Mass density and Poisson's ratio is given. Plasticity von Mises model is used, and we are providing a stress strain curve. Okay, a stress strain curve is provided. Ensure appropriate units are selected, and you can import or copy the stress strain curve from the data that you have. So in this particular training manual, we have kept it in the Excel sheet that can be copied and pasted over here. From the graph, you can see that it is quite smooth, and we have ensured that the points are appropriately representing the setup. So this is what it is about material properties and creation of the mesh or the setup. Next important thing could be in terms of the properties in here. So I'm not going into the area wherein we are doing a incorrect analysis in this particular lesson, and thereon we suggest what are the improvements that need to be done. So I'm directly talking on the point wherein the analysis has failed and we are doing the necessary improvements. So there are multiple reasons why the analysis could fail, and one of them is in such large deformations. Typically when the punch starts working, it can happen that in the first iteration itself the stresses are so high that they are crossing the yield limit, and the software thinks something is wrong and it will stop. So over there we are looking, or one of the suggested things is we reduce the initial increment. So typically if you see here, we are reducing the initial increment and as well the maximum step size. But the default step size or the maximum could be comparatively higher when you create a new study, and we are ensuring it is as small enough as possible so that the iterations continue with a smaller maximum step size, and if at all it has to step back, then we are going up to a small step size of 1e minus 8. As well, the number of adjustments has been increased to 20. So you can see the amount of flexibility and accuracy or the small time steps that we are giving here that will ensure that the solver setup converges well. Okay. Second, obviously this is a large displacement formulation, so that has been selected. Large strain option has also been selected, so that will help in of course I think it is common sense that this would be a large strain problem, so we need to select that as well. When we get into advanced options, no much difference. It is force control algorithm, iterative technique is Newton-Raphson, and integration would be Newmark integration. So that is left at the default thing. All other options remain the same. So this is about the properties of this setup. We saw plain strain elements being used. The material have been applied. In terms of die and punch, no much. It is a standard material, so that's fine. Next important thing would be in terms of contacts. First of all, the global condition has been edited, and allow penetration has been made. You can as well delete this option also because it has no much significance here. And we are creating local contacts down here. Okay, local no penetration contacts have been created. The first one is between the die and the specimen. Okay, the specimen and the die. We are selecting surface to surface no penetration contact, and the second one is between I'm sorry, I did it other way around. The first one is between the punch, okay, the punch and the specimen. That's it. Again, surface to surface condition has been used. So this is how the contacts look like and would be required in this setup. Next would be the boundary conditions in terms of where we are holding it. So in this case, the die is typically expected to be quite strong, so we can as well hold it directly at that location where it has been held, or else the other surfaces which are away from the place where this contact is happening, like this one and this one, they can also be used to hold this geometry. So basically die is quite strong, and that's what has been thought of here, and we are holding it firmly over there. Second one would be the symmetry conditions. This is a symmetric setup, so we can specify the appropriate lines here to define the symmetry. Okay, and finally punch. It is not the force, but we are actually pushing it down, and that one is represented by a setup wherein we are applying forced displacement. And if you observe here, we are moving from a value of 0 to minus 13, and thereon we come back to 0. So this is what it is. That is, it is pushing it all the way down and then it comes back. So that's what is happening for the punch. It is going in the negative y direction. Appropriate directions have been selected, and the solution runs for 1 second. So we are moving from 0 to 0.5, where we go to the peak and we come back. Okay, so this is the setup all about. And now what remains is in terms of force. Now this is not a load which can be easily interpreted, but typically imagine, if I'm not sure if this image captures that, but no, not really. So typically these specimens are quite long, and sometimes they are being held at the end for certain stability, so that they don't fly off, or they provide certain amount of restraint to the specimen. So in this case, in our setup, we are actually applying a force at the top of the specimen over here, that is going to hold the specimen at the appropriate location, and thereon that can help in stabilizing the setup. So this is a funny thing. I have seen users doing many mistakes. Some people even apply restraints over there, which is incorrect, because there can be certain amount of movement in the x direction for this part. Okay, the specimen can move in that direction, so we cannot use that. So keep those in mind, and this is a intelligent way of applying or stabilizing the specimen. Next, let's get into the meshing part of it. Appropriate local mesh controls have been given, and if I just plot the mesh, that should show you the way it is created. Quite fine, refined, especially at the contact cases, etc. We are ensuring that quite a good mesh is created. Okay, this is the way it looks. Now what remains is more towards the results. Okay, this analysis obviously takes some time. On my machine it took around 30+ minutes to solve. Luckily we have the direct, like last few minutes I was solving, and I have the results here. We'll get directly into the results. Okay, displacement. So first of all, displacements. This is at the initial time. Let me get it to the final time probably. Okay, I missed out on something, but before that, let me get it over there. Okay, this is the way it looks. So at 1 second, the punch has gone all the way till down, and it has come back. Let me animate this. That will show you how it goes on. So as you can see, the punch is pushing it. It goes on all the way. So there are too many frames, so it is telling me to try a smaller frame. That's okay. I'm not getting into it now. So we can play with it. So this shows you how it is going to work. I would also like to look at the point where it is 0.5 seconds. Okay, you can see the punch is at the most bottom point, and that's the way it would be deflecting. And this would be more in the form of displacement. Before I get into the stresses, I would like to highlight here, under result options, we are not saving the stresses for all the points. However, the stresses have been saved only at the start point of 1, end point of 10,000, and an increment of 60. So that the solution, the result file size is comparatively small, and we can actually get more accurate results, or enough accurate results. That's the way I would put it. Now let's get into the stresses. Of course, we can see one measure stress, but in this case, the X normal stress is far more relevant. And after plotting, and if I zoom in here, typically the blue one is the negative one, and is telling us that part of the area is under compression, whereas the red one is the tensile one. So that clearly tells the difference down there, how the part is being subjected to. In terms of equivalent strain, this is at 1 second, that is after the load is released, there is certain amount of permanent deformation, and we are seeing certain amount of equivalent strain that remains in this particular setup. Now when I get into equivalent strain, we do have the option of seeing total, or it can also be plastic strain, that is total plastic strain can be seen here, or it can also be elastic strain that can be visualized. So this shows you, this splits the strain into multiple different things, and we can actually visualize how much amount of plastic strain or elastic or total strain is present in this particular body. Obviously punch and die come back to their original location and they're fine enough, whereas the brass component is going to be subjected to certain amount of plastic deformations, and that's what we are studying here. Other results, of course, we can see the X normals at and further details. So this is fine. These are the same things, so that's fine. I think in terms of graphs, there are different results which could be significant. One of them could be the reaction force. Reaction force at the top of the geometry here somewhere. Let me take the appropriate location and plot it for you. Here somewhere, and update, and let me check if the graph looks like. Oops, there are too many points down there. I will try to take a single point and plot it for you. So that would be somewhere here. Okay, let me check how this graph looks. No, this is not that legible. Let me try to take it in a certain direction so that we can see it in a different way. Okay, let me try to see why is important. Yeah. So let me try to plot those things appropriate. So yeah, when we select that appropriate thing and when we click the response graph, we are actually selecting the top edge down here. The red line is showing us the reaction force on the selection, and the blue one is on the global thing. Obviously global one can neutralize so that there is balance and it is following properly, whereas the red line shows you the variation of the how can I say, the variation of the reaction force or the force required by the punch over a period of time. So you can see, to have that appropriate deflection, the punch needs to go until minus 25 newtons, and thereon when it is released, it yet sustains certain amount of force because of the pushing of the component, and thereon it can go down up to 0 once it is in the original location. So this is a useful graph which we can see and understand the force required by the punch to create this particular setup. And on the other way around, this is what it is all about. Let's go through the training manual because it has a lot of content in terms of explanations and discussions. If I missed out on anything while discussing this topic, then I can get to know from there. Okay, let's see that. What else is there? Defining plane strain, we understood. What is plane strain, you can explore. Giving the hardening factor is fine. We enter the stress strain curve, ensure that the units are appropriate. Okay, and punch and die, get global contact conditions. Contact sets have to be created appropriately, that's what we saw. We are holding the die at an appropriate location. We give the symmetry conditions. Excellent. At the top we are giving the translation 13 millimeters. It is given using a graph, that is from 0 to 0.5, that 13 millimeters is applied. Enter stabilizing force. So this force is a intelligent thing that we are doing to help stability of the component. It is a minute force of 1 Newton, so will not affect much. Mesh controls have been given to ensure it is mesh is created well. Mesh the model, and yeah, here it goes. So we discussed about the different time stepping options that have been used. So if you see this image down here, initially we start off with the default thing of 0.01, and max of 0.1. Number of adjustment has been just increased from 0 to 20. Other two things remain the same. However, in the setup we saw, and to ensure convergence, we have increased it to 0.0005, and max as well remains small at 0.0005. Okay. Obviously, when we are in this setup, we are giving the settings, solving, we see a failure, and then we improve the setup. Large strain formulations have been used. Use large strain formulation. Yes, large. Obviously, it is understandable that this setup is of large strain, and that's why we use. So we do that. We solve it. We see a failure, and then we go back. And change certain things to get back this analysis on track. On failure in this setup, we are seeing actually the von Mises stress comparatively even at the first small step itself. It is as high as 78.69 megapascals. So that could be one of the reasons for the failure. The first time step that the software took was comparatively very high, and that led to the failure. Convergence problems, singularity elimination factor. Yeah, so there are different things which can be done for convergence or helping convergence, and one of typical errors would be more towards singularity elimination, or under advanced properties we change the value of the instability factor. So here is what we are discussing. I think auto stepping, you understood the changes that we have done. We have reduced the maximum time step size, as well as we have reduced the initial time increment, and the number of steps has been increased to 20. In terms of convergence, if I show the option somewhere here, let me close this. If I go down here, this value has been changed. Okay, this value has been changed, or can be changed as well, from 0 to 1. That can help in convergence. The other thing are these values which have been changed appropriately. What else has been done? Yeah, this advanced option, the change down here, let me close this graph, it is not required, is more towards the maximum strain, which is been increased to 0.1. If I remember rightly, it was around 0.01, whereas now it has been increased to 0.1 to help for convergence. So we do expect comparatively large strains in this model, and it's fine to relax this particular strain value. And in terms of result options, even though in the study we have taken 60, but this setup is talking about 30 increment, so that will help in reducing the file size. Instead of capturing for all the steps, it is better to capture for certain steps. You can have a plot of von Mises and check it. May not be too much significant in this setup. However, it shows whether it is crossing yield points at certain levels or not. Yeah, the von Mises is being checked at 2 different time steps. Thereon, as I told you, we move into X normal stresses. Here we can see there is huge at the appropriate location there is compressive, and other way around it is tensile stress on the other end. Okay, we can as well probe the values on the one of the edges over there, and actually plot the variation of the normal stress along that edge. If you are curious, I can just show you how it works. So I have this thing. I can right click. This is at 1 second. That's okay. Let me probe it here. I select this, and I can update on selected entities. Yeah, on selected entities, I can actually update the results over here. What's strain, normal, edit definition. I would prefer it as the maximum point, which is 0.5, and I will accept it. Let me try to probe it again and select this one. Yeah, it is selected, and I can take this graph. Is it only at location on selected entities? I select this. Edge is not selected appropriately. Let me try to update it. And then I do this. So it's not smooth. It is definitely not smooth, but you can see the way the strain is moving from a positive to a negative value. or I think more of, am I seeing the strains here? Yeah, I would like to see the X normal stress. That would be more useful down here to understand if I try to plot it. Um, Let me check if this is a point. Yes, this is a point. I would like to see it on the entity. Let me plot it on the entity, and let me try to get the graph down here. So here it is. This is similar to what the training manual is talking about, wherein at the top we are seeing negative normal stress and it goes on up to positive on the other side. So that shows you the variation of stresses down here. So this is the graph. You can as well probe and see the variation over a period of time. That can also be a good thing. In terms of contact force, there is a good discussion down here telling that we are actually talking of a concept called as 3-point bending, wherein the part is bent using three-point locations, and that's the way it proceeds. So we get a good understanding of how it works down there. Strains, we discussed this. We talked about total strain, plastic strain, and elastic strain. That's what we can capture from this setup. If you are curious, you can also solve this setup without using large strain formulations. That can give a good idea of how it works. And what else is there? Plot maximum punch force. Yes, this is what we plotted. We can have a reaction force plot at the top surface, top edge, and see how the reaction force varies. So here it is quite smooth. It goes up to a value of 70 plus, and then it falls down. That can be. This is what we saw then. And okay, yeah. In summary, if you want, you can actually. So in summary, we saw that out of the different things, one of the important uses would be the reaction forces that are coming. So these reaction forces can be used to design the load cells or decide how much force to be applied. The reaction force graph can be exported and can be further interpreted. Obviously, the setup that we have is actually half model, so the reaction forces would be 2 times, or the forces to be used in the load cell would be 2 times this particular setup, and yes, pretty much that's it. That's the way it would actually work. So these questions are easy. I believe you should be able to answer once you have gone through the setup. There are 2 more exercises in this lesson. Please go through it. Very good ones. Again, it is a similar thing of large strain. Again, it is from the same university. It is a good example. And finally, there is a bit of text on the difference between true and engineering stress strain. If I to tell you in quick words, engineering stress strain would be more towards the strain that we are talking, or the stress that we are talking, which will consider the cross section at that moment, that is after a certain amount of deflections have happened, the cross section of the specimen will change. Whereas in normal, the stress strain that we typically talk of, it has a constant cross section, which is not true. Engineering stress strain is the real one, and is actually considering the cross sectional changes that are happening, and these images show that particular thing. So that should help me conclude on the nonlinear training. Please go through this entire training manual. I'm always there to answer any of your questions. Hopefully this new way of training is of a great use, can help you go through the content repetitively, as well as you can understand the things in a different way, in a more detailed way, at your own pace and time. Okay, thanks a lot. Look forward to meeting you in the dynamic analysis lessons.